Okay, this is going to be the last lecture for new material for the entire semester. At most, you've got to take the Chapter 7 test and possibly the final exam. The final exam is a completely optional test, and after I pass back your test from Chapter 7, you should know exactly what you need to get on the final exam to improve your grade and what grade you'd have if you skip the final exam. So the final exam is completely optional. Nobody has to take it, and there shouldn't be any question as to what your grade would be if you skip the final exam and what you'd have to get on the final exam to improve your grade. The final exam can't hurt your grade, so if you had enough points for a B going into the final exam, took the final exam and got a 0 on it, you're still going to get that B. So you can't hurt your grade to take the final, and I can certainly help you figure out exactly what you need to help your grade on the final exam. So, you know, if I don't make that completely clear to you when I pass back your Chapter 7 test, you know, to corner me and make it completely clear to you what your grade's going to be if you skip the final and what you need to get on the final to improve your grade. So this is a section of word problems. The word problems might look a little bit intimidating if you just glance at them. I kind of messed up here. I had an X in a parentheses that was supposed to be a T, so I just changed it. The stupid thing is I started doing this lecture about 10 minutes ago, and I started doing this problem, and the letters I had written in the problem probably weren't the right letters. I had P's instead of V's, and I had X's instead of T's. So I went back to my office, changed everything, and sat down to do the lecture again, and I didn't change everything. So I don't know. So hopefully that's not a sign of horrible things to come. But anyways, so the word problems may look intimidating. By the time we get through this section, hopefully they don't feel intimidating. The idea, every single word problem, somewhere in the word problem itself, like for problem 2, for problem 4, or problem 6, somewhere in the word problem itself, there's a formula, or somewhere in front of in instructions for a set of problems, there's going to be a formula. So like if I look at problem 8, there's not a formula, but there's a formula in the instructions that apply to it. So for every problem in this section, there's a formula that applies to that specific question. All we're going to need to do to get from the problem to the answer is understand what each of the letters in the formula means, understand the number that's given in the problem and how it relates to the formula. We're going to plug that number into the formula. We're going to use our calculator to get the answer. And it's not going to be a mystery, hopefully, what the variables in the problem, in the formula that's given for the problem mean. So the formula in this problem was supposed to say this, and eventually it will say it. I go back to my office and fix this correctly. And this little header part right before the formula actually tells me what the variables mean and kind of how the formula works. And the first thing I see is the value V. So this V stands for the value of something, and it's the value of a Raptor, my brother's favorite truck. So so what this formula can give me is the value of a Raptor that is T years old. So the T stands for the age of the Raptor in years. So just up to there, without having the formula, I understand that the letters in the formula, there's 2 letters. One stands for V, one stands for how much the Raptor is worth, the other stands for how old the Raptor is. So if I did something like this, V of 3, and I'm not going to do that, but if I did this, and entered this on my calculator, what my calculator is going to return to me is the value, V, after 3 years of the raptor. So when you plug a number in for t, the t stands for the number of years, and on the left side I can read this the value after 3 years, and on the right side I'm going to reduce that to some dollar amount. To answer the question, I'm supposed to find the value of the raptor in 6 years, so it wouldn't make sense to waste my time plugging 3 in, because plugging 6 in is what I need to do. So doing this, going to the t and changing it to 6, would make me read the left side of the equation. V stands for value of the raptor, 6 stands for 6 years, so the value of the raptor in 6 years can be modeled by 42,000 times 0.93 to the 6th power. Every formula in this section is probably more or less for informational purposes only. I almost guarantee if you went out and bought a raptor and it got to be 6 years old and you used this formula and said, well, my raptor's supposed to be worth this much, it probably is not going to be worth this much. I just made the formulas up so that they were, kind of reasonable, so that we didn't get ridiculous answers. But they are just completely made up formulas and have probably nothing to do in reality with the actual value of a raptor or whatever the word problem is relating to. So they're completely contrived. You can go home and tell your girlfriend or boyfriend, hey, we can use this formula for something any more than solving a problem in this class. So I'm just going to do this on my calculator, round to 2 decimals. So I'm going to go 42,000 parentheses 0.93 parentheses exponent 6, and my calculator gives me $27,173.59, because that 8 right there is the number of cents, and I'm going to round it up to 59 cents because the number after it is a 7. So my answer is going to be the value. It'd be nice to write words like this, but if you just put the number with a dollar sign, I'd live with it just fine. And I have no idea what a 6-year-old raptor is worth. I'd have a hard time believing it's worth $27,000, but I don't own a truck, and maybe worth more than that for all I know. But according to the equation that we're given, your answer is only as good as the equation that you're using. And it may not be a stellar equation, but it's the correct answer for this problem. And at least it didn't tell me the value was $2 million or the value was $150. So at least, I don't know that a 6-year-old truck is worth $27,000, but maybe it is. So again, for each one of these problems, I'm going to hunt down the formula. Before the formula, there's going to be some words that tell me how the formula works, and they all kind of are the same, kind of have the same feel. So the beginning of this problem, help me understand the formula. P of t equals to 2 million times 2.3 to the t power. So the first thing I see is a colony of 2 million bacteria. This 2 million, it represents the 2 million bacteria that are in some culture dish, I imagine. So it's growing in a culture medium. And I must have borrowed these words from somewheres, because I haven't had science since, 84. So it's been a long time since I've had science. No way how to break out these words by myself. So anyways, the 2 million in the formula represents just the number of bacteria that were in this culture at some given time. And then it says the population, which kind of means how many bacteria after t hours, is given by this function. So the P stands for the number, the population, And for the population, I'll say it's just going to be the number of bacteria in the culture. So the P stands for the population, or the total number of bacteria. And the T stands for hours in this case, as opposed to years. Because bacteria, maybe these bacteria are growing pretty fast. So in this culture, there's 2 million bacteria to start, and the formula will help me know how many bacteria are in the culture after a certain number of hours. And in the formula, on either side of the formula, there's a T, which is good because in the sentence that I'm asked to work with, find the population of the culture in 12 hours, I'm going to plug 12 in for T because that stands for the number of hours. And when I do the formula, I go P of 12. This says the population, or the number of bacteria in the culture after 12 hours, equals to, and then 2 million times 2.3 to the 12th power. My guess is when I enter this on my calculator is going to give me an answer in scientific notation, and I'm going to take the answer out of scientific notation by dragging a decimal to the right. I'm going to insert an implied decimal and drag it to the right. So I'm just going to enter this, and I'm going to round to the nearest million. Hopefully that's easy enough to do. So 2 million, 1, 2, 3, 4, 5, 6, times 2.3 exponent 12th power. I figured out, what a horrible number. So I get 4.382924886 times 10 to the 10th power. Not that that's there, now it's readable. So that's called scientific notation. If you've taken a science class on campus, you might be familiar with scientific notation and how to get your scientific notation answer out of scientific notation. When the scientific notation has a positive exponent, to get the number out of scientific notation, you need to take the decimal in the problem and move it that many places to the right. So to get this out of scientific notation, I'm going to have the same numbers, 43829248886, but I need to move the decimal 10 places. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need to move the decimal 10 places. And for 9 places, I passed up numbers that my calculator gave me. For the 10th place, I need the decimal to be out here. And to get it out here, I need to put a 0 in the space that I didn't have a number in. Now I'm going to backwards. Back 3, comma, back 3, comma, back 3, comma. And I read this as 43,829,248,860. But it says round to the nearest million, and the 9 is in the millionth position because this is 43,829,248,860. I can't imagine on a test asking you to round to the nearest million. Probably will kind of round to the nearest dollar because that's easy to do, but it's not a bad skill to be able to do. To round something to the nearest million, you go to the millionth position, you look to the number after it in the 100,000th position. If it's 5 or bigger, you round up. If it's not 5 or bigger, you don't round up. So I'm not going to round up to 43,830,000,000 because after the 9 million part of this, the number is less than 500,000. So I'm going to write for my answer 43,829,000,000, and I'm going to throw 6 zeros down because that's rounding to the nearest million. I don't need, so it's 43,829,000,000. That's rounding to the nearest million, and I'll just say bacteria, or maybe bacteria in the culture, but after 12 hours, and that's even getting wordy. But as long as I see the number and maybe a word like it stands for the number of bacteria in the colony, I would be content with, you know, any sort of answer as long as it has the right number and I understand that that number refers to the number of bacteria in that colony. 6 gives me a formula that somehow kind of broke up when I made it bigger font. So this is the formula, and I maybe didn't do the best job of presenting what the letters in the formula mean. So I'm going to have to really think about this a little bit. The T is the easy part. You notice I didn't write the left-hand side using function notation. It might have been nice had I said this was A of T equals to 500 times 2/3 T, using kind of a function symbol for the left side rather than just doing a single letter. It's not uncommon to see mathematicians get lazy and not use kind of a function symbol when they write an equation to represent a situation, but it's also not uncommon to use the function notation. But because I'm not given the function notation, I'm not going to use it. The T is the easy part of this. The T something is something for the number of years. So the T stands for a number of years. And what does this function give me out? It gives me out the amount of radioactive material present after T years. So the problem's a little more abstract, but it says we start with 500 grams of radioactive material, which is that 500, and it decays. When you have radioactive material, it's decomposing over time because it's unstable. And this formula, it's going to tell me over time how much of the radioactive material is left because it's decaying, it's losing, it's unstable, and if I wait long enough, that all that radioactive material is going to be gone. So what the A is how much of the radioactive material remains. So what this formula gives me, based on the number of years, how much of the initial 500 grams of the radioactive material remains, and I'm supposed to find out how much of the radioactive material is present after 10 years. So I'm going to plug in 10 for T. Even if I didn't really understand the problem, we use T for time frequently, and in this case the T is measured in years. The number that was given in the problem other than the equation was given in years, so I'd assume I'm plugging that in for T. And what I'm going to get out is how many of these 500 grams are left. So I'm going to go 500 parentheses fraction 2/3 parentheses exponent 10, and it says round to 1/10 of a gram, which is 1 decimal place. So after 10 years, most of this is gone. What I get is 8.67 grams, rounding to 2 decimal places, of the 500 grams are left. But it says round to the nearest 1/10 of a gram, which is 1 decimal place. So either I'm going to say it's 8.6 grams or 8.7 grams. And because the number after the 6 is 5 or bigger, I'm going to round up that 6 to a 7. So my answer is there's going to be 8.7 grams of those 500 grams that we started with will be left. And again, if you just wrote the number with the single word grams or something that I understand, that's what the 8.7 represents material, just a word would be fine. So the next few problems are a little more advanced, but not terribly hard. The problems 7, 8, 9, and 10, and really even the problems after that, then the next group of problems, use a similar formula. And in this formula, it's a generic formula that works for a number of problems that have a quote-unquote exponential growth. And so in this formula, the p sub 0 on the right-hand side of the equation is going to be the starting amount. And it's going to vary from problem to problem what that starting amount refers to. In problem 8, we start off with 1,000 computers being infected by a virus. The starting amount is going to be the 1,000 computers infected by a virus. When I go to problem 10, it says the number of daily visitors to Amazon is currently 100 million people per day. The starting amount is going to be the 100 million people that are going to Amazon each day. So the p sub 0, it's going to be given in the problem. It's the beginning number. And then e is something that's snuck on my calculator that I'll have to show you because we haven't done logarithms. E is just, it's not an unknown. E is on my calculator, and to get E on my calculator, there's two ways to do it. I can hit the alpha button and the x10 to the x key, and that gives me an E, and then I could put an exponent with it, because in this problem the E is going to need an exponent. Or there's another place that my calculator has the E hidden above the ln key, and if I hit the shift key and ln, it gives me E and it gives me the exponent. So alpha E gives me an E. I could type the exponent button to get E and be able to type an exponent. Shift ln gives me an E again. And again, that's something, E is related to the logarithm chapter that we don't cover anymore, that you'll cover if you take Math 151. So the E is not an unknown, it's just a feature on my calculator. The R is the growth rate, and I need to make it into a decimal. And somewhere in each of these problems, there's going to be a rate that the item is changing. In number 8, 3% is the growth rate. When I glance at number 10, 0.25% is the growth rate. And so it's just a percent that's given in the problem. And the last letter on the right side, the T, is going to stand for time again. Could be time in years, could be time in months, could be time in days. It's going to vary from problem to problem. And what's going to be gotten out on the left side is the future of how big the starting amount grows to. So it's the the ending amount, I guess. The P of T, we'll call it the ending amount. And that's usually what we're solving for. So each of the problems, 7, 8, 9, and 10, use this generic formula, but I need to take the generic formula and model it to the problem that's given. So when I go down to problem 8, I need to work the right side of the equation with numbers that fit the problem. I kind of need to understand the problem. So this problem 8 talks about 1,000 computers getting a virus, and that virus is being spread from one computer to another computer, and over time more computers are being infected with the virus, and I'm supposed to find out what the ending amount, after 10 days, how many computers are going to wind up with the virus. What I'm going to do is I'm going to take the numbers that are given in the problem, the 1,000 computers, the number of computers that are being infected per day, and the number of days, and plug them into the left side of the formula, and the right side of the formula, and break out my calculator. So the first number I see is 1,000. That's the starting amount of computers that are being infected, and that's going to be the P sub 0, because the P sub 0 is the initial, our starting amount. In this case, refers to the number of computers that have been infected with the virus. The E is the letter E. The R is the growth rate. And 3% I need to make into a decimal. This 3 has a decimal that's implied but not written after the 3. And to make a percent into a decimal, you need to drag the decimal 2 places to the left, which means I have to insert a 0. And the decimal version of 3% is 0.03. And then the last number I see is 10, and that stands for the number of days, and that's going to be the t. So in the exponent, I either need a times between the 0.03 and the 10, which would work, or I need to plug the 0.03 in a parentheses and a 10 in a parentheses for my times. I'm going to sneak that 10 on the left side as well. And I kind of read this as after the number of computers infected after 10 days can be found by this, and I'm going to round to the nearest 1. So I'm just going to put that on my calculator, round to the nearest 1, because it says round to the nearest integer, and that's going to be my answer. So I'm going to go 1,000. And then I need an E with an exponent, and the easiest way to get that is to go shift and ln, and my exponent is going to be parentheses 0.03 parentheses 10. And now it's going to give me 1,349.85 computers. And you can't have 0.85 computers, so this 8 is going to tell me to round 49 up to 50. So my answer for number 8 is after 10 days, there'll be 1,350 computers infected. Ten's going to be a completely different setting, but we're going to use the formula and kind of use the formula the same way. So as I read through 10, talks about Amazon, and again, these are completely made up numbers. I have no idea how many people go to Amazon every day, but it says right now 100 million people go to Amazon every day, and it's growing at a rate of 0.25% per day. How many people are going to be going to Amazon in 30 days? So the 100 million people, that's what I'm going to put in for the P0. That's the beginning number. The R, it's written as a percent, and it needs to be written as a decimal. To get any percent to a decimal, you drag the decimal and drag it 2 to the left. So I'm going to need to write 0.0025 for my R. The T is usually time, and that's good. In this case, it's going to be 30 days. And what I'm going to get out by going P of 30 equals in 100 times e to the 0.0025 times 30. What I'm going to get out is how many people in millions, because the 100 stands for 100 million people, how many people are going to Amazon in 30 days. So I'm just going to shove that into my calculator, go 100, shift and ln, and then parentheses 0.0025 parentheses, and then parentheses 30. And that, I'm not sure if you can really see that this morning, that gives me a 107.7, so I get 107.78. It says round to the nearest integer, so this 7 is going to round that up to an 8, and my answer is going to be 108, and since the 100 stood for millions of people, it's going to be 108 million people per day. Again, the word problem is just kind of for educational purposes. I have no idea how the number of people going to Amazon is growing from day to day, nor how many people go there, so it's just made up. The next formula is almost essentially the same. The formula that we get for 11 through 14, the only difference between the formula for numbers 7 through 10 compared to this formula is the negative in front of the R. When the formula that is an exponential function has a negative in front of it, what it does, it makes the beginning number get smaller. And so if I read through, the variables will stand for the same thing, and what I'll get out is a smaller number. So this talks about, in problem 12, there are 50 million people that support smoke, who smoke. Again, I fixed these problems up, but apparently not all the way. So there are 50 million people who smoke in the USA. This number is decreasing by 3% per year. How many people will, there's no question yet, smoke in the USA in 5 years? So it's an incomplete problem. I thought I fixed all the mistakes I had in my homework, but I didn't. This is the first time I'm teaching this section, so it's obviously not perfect. So the number of people who currently smoke in the United States, should say, is gradually decreasing. There are currently 50 million people who smoke in the USA. This number is decreasing by 3% per year. How many people will smoke in the USA in 5 years? Again, I have no idea. I hope there's not 50 million people that are smoking, but it could be. So just like the last problem, the P sub 0, or the last formula, stands for the starting amount. So there's 50 million people currently smoking in the United States. And the R, it's decreasing by 3% per year. I need to change this R into a decimal by taking the decimal that's implied after the R and dragging it 2 to the left. And then the part that I snuck in, how many people will be smoking after 5 years, I'm going to plug a 5 in. And for my formula, I'm going to go P of 5 equals to 50 million times e to the negative 0.03 times 5. I don't even say where to round. I'm going to round to 1 because I didn't finish this problem completely, or I didn't copy and paste it right. I don't know what my issue was, but I'm going to use this formula. I'm going to round to 1 just because I don't know what else to do. So 50 million times shift ln, and then parentheses, oh, forgot the negative sign, negative parentheses 0.03 times 5. It's got to be a number less than 50 million. And I couldn't have done that right. I forgot the decimal with the 0.03. Let me enter it again. So 50 million, 5, 0, and then 1, 2, 3, 1, 2, 3, 6, 7 zeros, and then shift ln, negative parentheses 0.03 parentheses 5. Better, I suppose. And that gives me 43,035,398.8 people. I'm going to round that up to 399 because, again, it doesn't say how to round. I'm going to round to the nearest person, and I'm going to say 43,035,399 people will smoke. And then so when you print this out, or when you open up my webpage, it'll be fixed, and you won't realize, well, you'll realize that I was a moron, but I fixed my issue. So using the same formula for 14, I'd see the 3 numbers in the problem. The 100 million is the population of some country, and it's the P sub 0. The rate is 2%, which I'm going to write as 0.02, and the time is 25 years. This formula is going to give me the population of a country that is losing population, like Japan or Belgium, where the population, I think, is decreasing. So I'm going to say the population after 25 years equals to the beginning population, 100 million, times e to the negative, and then I'm going to do 0.02 times 25. Just enter that, and I'll round to the nearest one person. So 100 million, 100, and then million, 1, 2, 3, 4, 5, 6. Shift in ln, negative parentheses 0.02 parentheses 25, and I get 6065306.97. So it's going to go down to 60,653,000. I'm going to round this 5 to a 6 because of the 9 after it. So I'm going to say 60,653,066 people for the population. And that's all there is for those last 4 problems. Basically use the same formula. The difference between 7 through 10 and 11 through 14 is that negative sign makes the number get smaller. If you don't have the negative sign in front of the R, the number gets bigger. The last group of problems, 15 through 20, use this. They help me figure out how much money I'm going to have in the future based on how much money I'm starting with. It's a more complex formula. And in this formula, I don't even explain the variables because I wanted to just take a second to explain the variables myself. So in this formula, the money formula, the A stands for how much money that I'm going to have in the future. That's usually what we're going to solve for in these problems. The P in the formula is going to give me the starting amount of money, and that's usually going to be given. When you have money invested, usually it's paid interest. The R is the annual, it's the interest rate, but we need to make it as a decimal again. And it's similar to the growth rate that we had in the last problems. I'm sure if you have a loan, you're familiar with interest rates. If you have a loan, then you probably pay interest every month. If you're saving, sometimes interest isn't computed every month. And the N stands for how often interest is computed. For instance, if it said interest is computed monthly, then the N would be 12 because there's 12 months in a year. If it said interest is paid every day, then the N in the formula would be 365 because there's 365 days in a non-leap year. If it said interest is paid quarterly, then the N is going to be 4 because there's 4 quarters in a year. The first quarter is January, February, and March. The second quarter of every year is April, May, and June. The third quarter is July, August, and September. And the fourth quarter is October, November, and December. So if interest is paid quarterly, it's paid 4 times per year. And if interest is paid annually or yearly, the N in the formula would be 1. So the N varies from problem to problem, and there's going to be a word in the problem that helps me understand how often interest is being paid. And the last part of the formula, the letter, is the T, and that usually stands for the number of years. So for each of the next few problems, I'm going to dig through the problems, get the starting amount of money, the interest rate, how often interest is being paid or computed, and a number of years. I'm going to shove them into the formula, and then I'm going to use my formula to find out the amount of money I'm going to have in the future. So for problem 16, as I read through the problem, I'll start to see numbers. The first number I see is 1,000. That's the starting amount of money, and so I'm going to plug 1,000 in for the P in the formula. The next number I see is 3%. That's the interest rate, and I'm going to have to enter that as 0.03. And then I see twice. It says interest is compounded twice per year, which means interest is paid or computed twice per year. And for the N, I'm going to put in 2 because it tells me it's twice per year. The last number I see is 10, which stands for the number of years. So I'm going to be able to tell you how much money this $1,000 is going to grow to in 10 years. By using the formula, A is the future amount of money, P is the starting amount of money, R is the interest rate as a decimal, N is how often interest is being paid each year, N again is how often interest is being paid each year, and T is the number of years. So if I just take those four numbers, plug them into that formula, this will give me how much money an account that starts with $1,000 will have in 10 years if it gets 3% interest twice per year. So I'm going to just break my calculator out and round to probably 2 decimals because it's money. So I'm going to go 1,000 and then parentheses 1 plus fraction 0.03 over plus fraction 0.03 over 2, close my parentheses, exponent 2 times 10. And my calculator gives me $1,346 and then 0.855 cents. I'm going to round that to 2 decimals, so I'm going to round it to 86 cents. I'm just going to write my answers with a dollar sign. So the amount of money this account's going to have is $1,346.86 after 10 years of getting 3% interest paid twice per year. Do the same thing for 18 and the same thing for 20. Using the same formula, the numbers are kind of written in the same order. The first number I see is the initial deposit, so it's the starting amount of money. The next number I see is the interest rate of 3%. And the 3% I need to make 0.03. And then I see the word quarterly and the word compounded. Compounded always refers to the n, and the word after compounded is going to give you a value for n, and there are 4 quarters in a year, so the n is going to be 4. The last number I see, 17, stands for the number of years. So I'm going to say the amount of money I have in the future equals to the $20,000 that I'm starting with times 1 plus the interest rate 0.03 over n, which is 4, to the n, which is 4 times t power. So if I plug that into my calculator, that will tell me for this particular investment how much money it's going to be worth in 17 years. Again, it's just a calculator problem now, so I'm going to go 20,000 times 1 plus fraction 0.03 over 4 exponent 4 times 17 power, and I get $33,242. I'm just going to round that to 50 cents because after this, the 50 cents, there's a 3 that tells me I don't need to round up to 51 cents. So my answer is going to be $33,242.50. Last new problem of the semester, we have the review left, but there won't be anything new on the review. Same formula. First number I see is $200,000. That's the starting amount of money again. Next number I see is the interest rate of 7%, which I'm going to need to make 0.07. Then I see compounded semi-annually, and that tells me the value for n. And semi-annually, I think that means twice per year, so I'm going to put 2 in for n. And the last number I see is after 15 years, which stands for t equal to 15. The only thing that's tricky is figuring out the value of n, because usually the value of n is given in words, and you have to translate the words that are given to numbers. The p, the r, and the t are physically usually given as numbers. So now I'll plug them into the formula. The amount of money I'm going to have in the future is based on the $200,000 that I start with times 1 plus r, which is going to be 0.07, over n, semi-annually is twice per year, to the n times t power. And I'll just pop the numbers into my calculator. So 200,000 times 1 plus fraction 0.07 over 2, parentheses, exponent 2 times 15 power, and whoa, $561,300 $358, and I'm going to write 74 cents because, again, after the 4 there isn't a number that wants me to round up. So my answer to problem 20 is going to be $561,358.74, and hopefully I did a proper enough job that you can go through the word problems without, without much of a hitch. If you can't, come visit me and I'll try to smooth out what I didn't do well enough today.